an expert in semiconductor design and computer architecture. Dr. Renival completed his SGS ITS in law and his PhD from IIT Indore. Organizations like USD Global, Intel, and IBM energy efficient memory architecture, input output circuit design, and pre silicon validation for IoT applications in advanced FinFET processes. Dr. Renival has received several prestigious awards, including the SIRE 2022 Faculty Fellowship from the DSP and the User Design Best Research Paper Award at the IEEE 29th Conference on VLSI Design. He has also been honored with the International Travel Award for his work in solid-state circuit design. Currently, Dr. Renival is an assistant professor at IIT Jodhpur, India, and has previously taught at BITS Pilani, Triple IIT Kanchipura. He will now deliver an expert talk on evolution of computing architecture for edge AI, a comprehensive review, and where he will share his invaluable insights into the latest development in memory architecture. Dr. Bhupen Singh Renival.
Thank you for the introduction. So, hi, audible? Very good morning, everyone. Thank you for this introduction and invitation to Dr. Deepika for inviting me for this Atal Fdp. So, actually, I'm going to talk a little bit about this emerging computing architecture, right? Particularly from the age AI point of view. AI, if you, AI is a very buzzing word from at least last half decade. And currently, last maybe 1 or 2 years, it is going to be one of the most search keyword you can say on the internet also. So we can say AI technology enables for wide application range.
On है. It's working.
So AI is one of the key driving force behind many sophisticated applications, including the neuromorphic computing, brain interface computing, our medical image processing are one of the very key hot, which is talk about the ADAS autonomous driving assistance systems, where like the object localization, detection, and classification is one of the very important tasks, right? Or we can say the human intelligence where we executed on the gaming console, right? So all these applications are actually driven by AI. And what is the difference between the conventional computing and the computing required for when we talk about the AI is the amount of data, correct? The enormous amount of data. So like if I give you one of the example in maybe earlier days when we go for purchasing a car, what basically we talk about what is the mileage, cost, and other things. But if you go to the car, the salesperson will give you that this having such feature of ADAS level 1, ADAS level 2. Have you heard about ADAS, automatic driving assistance system? So when we talk about the self-driving cars and all, okay, so when we definitely we need some vision for the car. So how when we say vision, then the computer vision comes in picture. Okay, computer vision in the sense there will be some involvement of the camera, radars, lidars, and all those things. So the monitoring the road, detecting the objects, classifying the objects, and it is a constant process. It's not, and based on the inputs, we basically take the decision. Like decision in the sense braking
Awesome.
system, turn and all those things. Correct? So, but
हाँ
you
बोलो
just understand how much a single image, if you take earlier our mobile phones and current mobile phones, where we talk in terms of the megapixels, 64 megapixels and something like this, the amount of
वही होगा
data
है
or
नहीं क्या
image taking and the amount of
कब
data
कोई ले गया होगा पता
coming
नहीं
from through the
मैं थोड़ी
constant
सी
video.
निकल गया
Correct? So, talk about such huge data, we need a
एक बार मुझे
huge
लग रहा है
amount
आपको
of
मैं
memory
प्रोड्यूसर
to
से बात
store
करनी
such
पड़ेगी
data and simultaneously to process this data. Right? So
मुझे
this
कभी
one
किया
like this is one of the application sets, but there may be multiple application sets of
नहीं
where.
मुझे
But
नहीं
now the difference is that this if the
सेंट्रल बैंक
amount of
में
data is more, we need the
ठीक है सर
different
मैं पहले ही निकल गया सर
architectures, particularly computing architectures, to store and process this huge amount of data with energy efficiency. Okay, so processing a data is not a big problem still, but it should be energy efficient. And when we talk about energy efficiency, particularly from some of the devices like IoT Internet of Things devices or the edge devices where computing happens onto the device itself rather than in the clouds, then you need energy efficiency in the sense like if your mobile doing some computing, it should not get
यस सर
drain the battery in 1 or 2
ठीक
hours
हाँ
or
सर
4 5 hours. Correct?
ठीक
It
ठीक
should
सर
run long. Correct? So that's why like energy efficiency
मैं
is one of the very critical parts. You can say very critical figure of merit you can say apart from the computing. If you look at so and go to the back, many of you have gone through some of the computing courses or computer networks and all. Since the last 3 4 decades, one of the very conventional computing architecture is what? It is the von Neumann architecture. I hope many of you are aware of it. And if you look at to the von Neumann architectures where most of the conventional computing rely on, if I say the architecture is that there is a processor and there is a memory, correct? And memory is sitting somewhere, processor is sitting somewhere. So whenever to be performed, the data first comes from the memory to the processor, which you call ALU, and the memory then in the ALU some operations will happen, and once the operation is done, again the data will go back to the memory. Correct? So like there are two things here: the movement of the data, which you call so fetching the data, fetching the instructions, because instruction is also ultimately a data. Correct? So fetching the data which involve the movement of the data between memory and processor. Now, if this movement comes in picture, there are two things. One is the latency involved in moving the data from memory to processor. Second thing, actually what is data? Data we define in terms of the bits, no bits, bytes and all. And one bit ultimately, and if you go to the very back end level, what is the bit? It's actually the signal, voltage signals. Correct? When this voltage signals go through on particularly on silicon, if you look at to how the data flow through the database is what? Actually, it's a interconnects, on chip interconnects, metal interconnects and all. So there is a movement of the data, there is a movement of the signal which cause the huge voltage drop, okay, which cause the power dissipation. So now we can say when we talk about this movement of the data, there are two things. One is the latency involved, and one is the energy or the power consumption. Correct? So this is one of the very severe bottleneck in current conventional, in the current application, particularly from the AI point of view. Because why it is a problem, I think we will see. That's why there is a need. We need a very specialized computing architectures. So that and this bottleneck actually called the bottleneck because the architecture is voluminous, the architecture is there, the memory is some computing, the movement of the data and the power involved, power consumption involved in movement of the data is one of the critical issues. So then we need some alternate architectures. So it's not like only people are working from architecture point of view. Ultimately, energy efficient computing people already had addressed at the various levels, including the like emerging devices where they consume less amount of power. Okay, some innovative circuit design techniques. Now since we have already explored a lot, if you talk from the Moore's law, we have reached to the level where people now finding difficult to more. Now that's why people looking for some architecture level solution. Okay, so where the concept of neural computing comes in picture. Okay, so neural computing actually inspired from the neural network. Okay, so a neural network actually inspired from your biological neurons. Okay, so now the question comes: what is the difference between conventional computing and okay? So if you see in the conventional computing, it's still we tell the computer what to do. No, we tell to the computer what to do, and computer actually break the big problems into a small problems, and it executes the task. But it's relatively different in case of the neural computing comes and it learns from the observational data. Okay, when we say learning, that's why when we discuss the neural network, we talk about the sophisticated terms like learning and all, learning the neural networks and all, right? Weight, updates, and all those things. And the system figure out its own solution, which is the part of training. Okay, when we say training the neural network, right? So there is a very clear cut difference between the conventional computing and the neural computing. It is having a various diverse set of applications starting from computer vision, speech, natural language processing, where now we are talking at the LLM level, to large language models in HGPT scenarios. Okay, so this is the conventional non-linear architecture. I think I have little bit talk about this, where you can say this is the memory, this is logic, where logic is actually just representing the of ALU that you can say, and whenever any operation needs to be performed, this data actually will come, and once the computing is done, again data will go to the back to the memory. Okay. So and other like building blocks, as you know, control units which control the memory and other. The number of registers is depend on what types of architecture. So this is one of the very conventional architecture. You can say the one Neumann. But one thing I think you should note from here that in case of the one Neumann architecture, we have a very one bus which carries the data and the instruction board. If you recall, maybe some of the computer architecture course, there is a bus which carries the data and the instruction board. Okay, but in the advancement of the computing, when the new architecture comes, which is the Harvard architecture. So Harvard architecture is solve the problem of latency in the way that it is having a very dedicated buses for the data and the instruction. Okay, so there is a some relaxation in terms of the latency, but still the movement is there. Okay, so like I talk about the two important figure of metrics. One is the power consumption. So it this architecture is good in many senses, particularly from the latency point of view, because now we have like it's like a two lane. We have one lane and now we have the four lane or six lane network. So one is dedicated for the data, another instruction set. But still the movement of the data is there because the key again the memory is sitting somewhere and the processing happens will be there. So we can cope up with the latencies at the some extent, but the power consumption is one of the issue is still there. But still there are many computing applications where processors are still used, including the RISC-6 on all ARM processor. If you look at to their architectures from the computing point of view, they are basically rely on the Harvard. So if you see here, particularly in respective of the architectures, and if you correlate enable all these applications. So we can say memory is one of the very integral part of the computing. And if you look at to try to understand the computing memory from the human anatomy, like in our we say we have the short-term memory loss or long-term memory. Right? Similar to the computing, if you look at to the human anatomy, where this cerebral cortex, one of the portion of the brain which is responsible for storing the data, and this also store the data, but it is store the data like short term. So that's why the concept of volatile and non-volatile is common. Okay. Similar to if you look into the computer we have the two different types of memory. Right? One is the volatile, another one is non-volatile. So can you tell which whether case is the volatile or non-volatile? It's a volatile. Okay. And what is the non-volatile memory element? ROM. Correct? Our hard disk and all those things are correct. So similarly, like if you look at to the computer, we have the two different types of memory here. So now, if you look at to the intensiveness of the computing which involved here, so if you look at one of the two very famous, if I give the example of one of the two famous neural network models, okay, there are multiple neural network models are there, but if you look at to the state of the art neural network model like the Alex, if you look into the architectures, the Alex actually consists of 16 millions of filter weights. Like, and in case of the VGG, even it is more complex, which is consists of 138 million filter weights. And these are just the filter weights, but when we talk actual about the operations, which is the convolution operation, which is the fundamental operations in all the neural networks, then it requires almost 724 millions of convolution operations in case of the LXNet and 15.5 billions of convolution operations. So now you can say how much, if you look into the top one, how much amount of memory we require to store the data, this 16 million of filter weights, correct? And in the operation, if you look at it, particularly from the LXNet point of view, it requires 724 millions of MAC operations, where MAC stands for multiply and accumulate, which is a very fundamental operation for the convolution. Okay, so because the convolution is one of the very fundamental operations which happens into all neural networks. Right? So the key point here is to note that the amount of enormous amount of memory required to store this data and the processing required to perform this, which makes the energy hungry computing infrastructure. If you look at to completely build this sort of applications with the help of von Neumann or the Harvard architecture. That's why we need something interesting or something innovative where the concept of term which is called in-memory computing. So from the name itself, you can say the in-memory. There are two terms. One is memory and another one is computing. Okay? So if I say the main philosophy of this, it's like making some smart memories. Smart memories in the sense the memory which stores the data and simultaneously able to perform some sort of computing. I say in-memory computing, it's not like we are completely going to replace your ALU or CPU. Are very still we are not at that level, but we are in a position to perform specialized operations inside the memory. And people are trying to explore and trying to build multiple algorithms inside the memories for particular tasks or particular application sets. So if you look into the AI, since this is in AI, like to the one of means fundamental operation is MAC. So people trying to implement the MAC inside the memory. MAC stands for multiply and accumulate, which is actually the convolution operation. Correct. So the concept of like you can say the memory here is that we have the processing unit and here we have the memory. Now we are actually avoiding the movement up the data and trying to put all the computations on the memory itself. So if you look at to like quantitatively try to understand very important data from some of the literature where we talk about the energy consumption and distribution in the sense the countries what we are talking about the Harvard or the one unit. Right? Here if you see it's almost like 48% of the energy is consuming and about 35 is for the computation percent and training is for 8%. So this is the data particularly from the if you implement the AI algorithms with the help of conventional computing architecture. So the amount of energy built these sophisticated algorithms with the help of this conventional computation architecture which talk about the von Neumann bottleneck. Correct? So if you go into more depth and take some of the example of particularly from the since I talk about two things latency and the power consumptions or energy consumptions. So if you look at to the first figure here actually talk about the amount of it's talk about actually the bandwidth of the various at the various abstraction level into your computing. So you can see that if you look at to this the bandwidth at the system bus level is almost in a GB per second, okay, which is goes at the if you talk about exactly onto the bit at the memory level data fetching, not to the IO levels or not to the I can say the buses level, which is almost in when we comes to fetching the data at the bus level, the amount of latency involved is like increasing like anything here. Okay. And similarly, if you look into the power consumption point of view, you can say at the memory bit lines levels in respective of the memory, particularly this is for the amount of accessing the data of the bits, it's sort of like picojoules. But when it comes to the system bus energy, where when we transmit the data with the buses to the maybe next integrated circuits through which we are communicating, the amount is need to like put it like we can say there is a very significant drop in case of like in case of the latency and the power consumption or the energy consumptions when you look into the different abstraction levels. So if we are somehow able to manage this, like avoid this movement of the data and do some sophisticated computing inside the memory, then we can address this bottleneck. That's why in-memory computing or the computing in memory or processing in memory, all these are the synonyms of this term, has emerged in recent years and many universities actually working very actively and also working very actively on this. Now let us say how neural computing actually works. If you go back, if you go back, if you go and recall your school days, how you learn the things in school or even school all, how actually you train them to understand anything. So if you look at how our brain actually learns in the school, how we learn that this is square, this is circle, this is triangle, like rectangles, right? So when we talk about learning of this, particularly in the there is the concept, there is the terms comes which is called the features. Okay, so we actually our brain learn these shapes based on their features like loopy circle or the square and all those things. Similarly, if you look at to the neural network, we try to mimic this learning which is inspired from the biological neurons with the help of artificial neurons. Correct? So if you correlate this to analogy, like see, if you want to like you want to classify these three images, okay, how neural networks actually have understand this, they understand based on the features, okay, based on the multiple features, and when you have the more number of features to classify particular objects, then you need different like more computing and more amount of data to store those images. Correct? So you can clearly like understand how our conventional learning happens in our students. Same, we actually try to train our computers, our systems to understand the image and to classify them. So first you understand, then only you can classify. Okay, so classification happens based on the multiple features. Correct? So all this actually inspired from the, like I told, is inspired from the biological neurons. So if you look at to the biological neurons, this is the very typical or very side structure of the biological neuron. Consists of various building blocks or the various like dendrite, nucleus, cell body, axon, and here if you see actually this is the nuclei of the your biological neurons, which takes the multiple signals. So here when we say signals, actually it's a biological signal. Biological signals in the sense when like electrochemical actions happens on your biological signal, generate some biopotential. If you remember about or if you know a little bit about the biological sense, how it's actually the shape of the voltage waveforms is there. Okay, which so this we actually call the biological signals are biological, which comes to this nucleus. So you can say this signals actually comes to the neurons nucleus of this biological neurons through with the various dendrites. Okay, so like you can sense the multiple signals, all these signals actually will come to the nucleus, and where all these signals get summed. So summed in the sense, in case of the mathematical language, we can say it all signals get accumulated are the sums, and if the summation of all these signals cross the particular threshold, then only these signals will transmit to the next neuron, which is called the in a more technical name the firing of the neuron. So this is the very like we can see the simplified working of the biological neuron, which how if you try to replicate this, I try to emulate this application, then the concept of artificial neurons comes, which is also perceptrons. Okay, so if you correlate these two things, so here we can say this x1 to xn are the multiple signals. Okay, all these multiple signals dendrites to the nucleus of this biology. Now, these signals, all these signals which are having the having importance are in a more technical language, you can say the weights. Okay. Like you can say the importance of these multiple signals actually will be decided based on their weight. 1 to Wn is the weight corresponding to the particular signals, and we get multiply the particular signals with their weight like x1 dot w1 or x2 dot w2 and xn dot wn, and we sum all those signals, right? And if this summation is crossing a particular threshold, okay, then it will neuron to the activation function. So this is the very typical functionality of the any artificial perceptron, which is actually inspired from the biological neuron. I hope many of you have gone through this. Some of the courses are out of your interest. So we can say when we talk about the neural network, the very fundamental element here is the artificial neuron or the perceptrons, and if you mathematically model this, it is actually multiplication of the two terms, and later we are actually summing the multiple of the yes weights. Right? That's why this is, if you mathematically analyze, actually it's a multiplication plus summation operation. That's why it is also called the math multiplier in accumulation. Right? And I'm not talking much about this B, which is the bias and all, maybe we will talk later. So we can say this is the fundamental processing element. Further, and we try to having multiple neurons, then how these neurons actually get interconnected, then the terms which is called the neural network. So neural network nothing but the how actually the multiple neurons are connected to each other, then the new network comes in picture. And when we move further, any neural network having particular architectures, actually it talks about the multiple layers of those neurons. Okay. So we can say, if I use the example, this is one of the example of neural network where this is the input layer. So input layer consists of the multiple neurons. So here we have the multiple neurons. Output layer. So output layer also consists of some set of neurons. And in between we have another layers depend on the architecture, how many number of layers you need, depend on what is your task and all. All this layer we are calling or classifying it. Okay. And so this the architecture actually depends whether the connected layers or the parts. This is the example, the example of the fully connected layer oriented neural network. Right? So let me give a little bit more about this. So this is the multi-layer neural network model. Okay, so when I say, since we in the previous here we talk about the single, talking about the multi-layer. Right? Multi-layer in the sense we have the multiple neurons here. So you can say these are the multiple inputs and they are actually getting multiplied with their weights, and this will will transmit to the next neuron, and if this summation actually cross the particular threshold, then only this neuron will get activated, and again one of the layer, and this is the input signal, right? And these are now we can say, since this is the one layer, we can say these are the various weights of that particular layer, starting from W1 to Wn. Fine. So this is the example of how the multi-layer neuron actually. So now this picture is interesting in the sense it talk about the multiple level of abstraction. Like a software engineer actually will be very first one. Software engineer in the sense of computer science students are people who are working in the very coding and programming levels. First image where they talk about the feature detections, object localizations, and other things. But this is actually a very like multidisciplinary or the multi-abstraction level problems. Also involve a lot of mathematics. Okay, so because if you see a simple perceptrons model, which is talk about the math, it's a simple mathematical model. Okay, so it's also involve mathematics. And this mathematics actually get complex when we talk about the multiple features. Okay. And the multiple features actually depend on the how complex is your image which classified. Okay. So if you look at to this try to understand from the algorithm point of view or from mathematical point of view. Next, actually, is simply a multiplication of two different matrices. Okay, so this is the one matrix, this is another matrix. The first matrix gives you the input signal, and the another matrix actually corresponding to its weight. Okay, and like the school days, if you see how actually the matrix multiplication happens with the first row and the first column, will give a one particular make operation. Now you can understand that the like if you have the more number of